Hello everyone, thanks for attending our presentation in the BMTT workshop. I am Yi Zhou, and our team also includes Jia Rui, Hao Tian, Hongmin, Cheng Qian, and Professor Zhenglen Huang. We are from the Information Processing Lab at the University of Washington, and we would like to introduce our method IA-MOT, Instance-Aware Multi-Object Tracking with Motion Consistency, which is a winner of the Track 3. First of all, I would like to give some background knowledge for this task. Track 3 in BMTT is a tracking-only challenge. It aims to track both cars and pedestrians with given detections and segmentations, and gap filling or running additional detectors are not allowed. As for the dataset, Track 3 contains the sequences from both KT-MOTS and MOTS-20 with various resolutions, frame rates, and viewing points. To evaluate the performance, SMOTSA is used to measure detection, segmentation, as well as the tracking quality. And finally, our proposed IA-MOT got the winner from the 13 teams with 69.8 SMOTSA. The pipeline of this talk includes the following sections. Firstly, I will give a brief introduction on our proposed method, and then talk about our instance-aware feature extraction from the given detections, as well as the instance segmentation masks. After that, our teammate Jia Rui will discuss about the following online tracking with short-term retrieval and RelD with motion consistency as a post-processing stage. Moreover, our implementation as well as performance on KT-MOTS and MOTS-20 dataset will also be explained later on. And finally, we will give a summary. This is the overall framework of our proposed IA-MOT. The framework can be basically divided into two parts. The first part aims to extract the embedding features from the provided detections. And using these embeddings, the second part mainly do the object tracking to obtain the final results. So first, images are sent into a mask RCN architecture with an actual embedding head to extract the bounding box embedding features for each detection. Second, spatial attention map or SA map for each detection is generated. And then they are applied to the bounding box embedding features to obtain the instance-aware embeddings, or we can say it IA embeddings. After that, these IA embeddings are sent into the tracking stage. A Hungarian algorithm is firstly implemented, cooperating with the STR to associate objects in short term. Then, RelD is used as a post-processing stage to connect the tracks with long-term occlusions. So let me first talk about how to extract the instance-aware embedding features using a mask RCN-based network. Based on the original mask RCN, we add another embedding head to obtain the embedding features for the later tracking stage. During the training, the three heads are jointly trained using the loss function. We jointly consider the bounding box loss, mask loss, and the embedding loss. The embedding loss is calculated on the instance-aware embeddings after the spatial attention is applied. Detections in different trajectories are treated as different classes and trained using the cross-entropy loss. During the inference stage, we use the given public bounding boxes as a region proposals and use the given public masks as to generate the spatial attention. The basic idea of this spatial attention is to do a filtering for the background information in the bounding boxes. So the intuition is that to get better embedding features, we want to keep the foreground features and suppress the background features. During the training, the spatial attention is generated using the mask head output, while during the inference, it is generated by the given public masks. And here are some spatial attention maps, example from the both Kitty MOTS and MOTS-20 dataset. We can find that our spatial attention can focus the original bounding box embeddings to the foreground regions. To illustrate the quality of our instance-aware embeddings, we show some feature visualizations. Using the MOTS-20 sequence 11 as an example, the figures on the left shows the average inter-object feature similarity and intra-object feature similarity with or without the spatial attention. We can find that it can be separated better with the spatial attention applied. So we can select 0.8 as the feature similarity threshold. The red figures are embedding visualization using the TSNE method. With the spatial attention in the training stage, we can see that the appearance features are distinctive and well clustered.
Here, I will explain how the detections are associated. Firstly, the given detections and the corresponding features in frame T are assigned to the tracks that show up in the last frame by Hungarian algorithm, which uses the mask IOU and feature similarity as the cost to minimize. Then the match tracks are updated, and tracks that find no matching detections are considered as lost. Unassigned detections and the lost tracks are reconsidered for alignments with looser constraints in the short-term retrieval module, STR for short. STR match tracks are updated and conduct possible bounding box interpolation. If not, then new detections will be initialized to new tracks. Besides, lost tracks are checked periodically to see if they are lost for too long, if there's no record for the previous N1 frames. These tracks will be marked as terminated and no longer valid for the above online matching. The cost function of Hungarian matching include the mask IOU between the detection of a live track in the last frame and current detections, and the cosine similarity of the features. The feature of a track is the stack of its first n and the most recent n frames, 2n in total. It is also common practice to use aggregated features. However, we found that due to the difference in visibility, size, and the surrounding objects, the temporal connection of the embeddings cannot be simply weighted and added up across frames. Also, averaging over the similarity smooths the correspondence and introduces ambiguity, so we choose the maximum number. While the short-term retrieval module handles missing detections, we also introduce tracklet re-identification as post-processing to deal with occlusions. First of all, if two tracklets do not overlap in time domain and they are within N2 frames apart, saying T1 and T2 as example, and their features are similar, they are considered as candidates for reconnection. Then, the Hilbert regression is used to extrapolate the interval respectively. The average IOU of the extrapolated bounding boxes is confined to be above the threshold. Meanwhile, the motion of each trajectory is defined as the average moving vector of the top left point of the bounding boxes in the last or first n frames. N equal to 5 or the trackly length if it is shorter than 5 in the implementation. The cosine distance of motion 1 and motion 2 should also satisfy the criteria. To further remove false positive in the given detections, including duplicated and objectless detection, we first apply confidence thresholding 0.3 and the minimum bounding box size filtering. In addition, for two overlap masks, if the overlap area is larger than 70% of the smaller mask area, the small mask will be discarded. For example, the man mask in red and his coat in blue overlap, and on the right, the lady is detected twice. Here, with the mentioned conditions, smaller masks are dropped, so false positive is reduced. Similarly, after tracking, we also use average bounding box aspect ratio for pedestrian, average confidence, and track IOU to remove non-target objects or duplicated tracks. Note that the car's aspect ratio vary a lot due to occlusion or truncation, so there's no aspect ratio constraint for car. Our proposed method is the winner of the 2020 BMTT Challenge Track 3 with 69.8 as MOTS-A. We are the first in MOTS-20 dataset and also have great performance in the Kitty dataset. Here are two examples in the MOTS-20 dataset. Our tracker handles occlusion well in no matter it is moving or static camera, or different object size. Also, the tracking is smooth with very few ID switches. These are two demos in the Kitty dataset. The tracking is still continuous in the scenes of turning or crowd parking on both street view and highway view. To summarize, our proposed method consists of three parts. First, features obtained from a pre-trained mask RCNN with the given detections as region proposals and masks as spatial attention. Second, Hungarian algorithm and the short-term loss track retrieval helps to connect the detections. Third, considering feature similarity, trajectory, and motion consistency jointly, the RelD module further reduced the chances of ID switch. In the end, we would like to thank our IPL group members and advisor Professor Zhenan Huang at University of Washington for their ideas and assistance. More detailed information will also be released in our lab website. Thank you, and we are very happy to take any questions.